In this video, we're going to look at angular momentum applied to fluids. The motivation for studying conservation of angular momentum comes from the application of rotating systems. We see such rotating systems in applications like pumps, compressors, and turbines. These are all very important mechanical engineering applications. In these types of systems, it's much simpler to look at rotating problems by considering the angular momentum. Using conservation of linear momentum results in an unsteady problem when we have a rotating frame of reference. So, let's recall the definition of the angular momentum. The angular momentum is a vector, and it is essentially the moment of the linear momentum. So if this here is the linear momentum, then we are taking the moment of the linear momentum. As we saw when we're setting up our conservation laws in an Eulerian frame of reference, i.e., when we are looking at control volumes, we are interested in the property that is being conserved per unit mass. So per unit mass, the angular momentum is simply the cross product of our moment arm and the velocity vector. If we apply the Reynolds transport theorem, what does that give us? So recall, typically we look at a uppercase and lowercase b, and we apply it to the Reynolds transport theorem. So essentially what we're looking at here is the material derivative of the angular momentum for the system is equal to the temporal derivative of the angular momentum inside the control volume plus the fluxes in and out. And let's remember, just like Newton's second law states that the time rate of change of the linear momentum is equal to the sum of the forces, the time rate of change of the angular momentum is equal to the sum of the moments. So this gives us the sum of the moments. So let's remember what these terms are all telling us. These are the fluxes in and out. And this is essentially what the control volume is seeing. So this is in the control volume frame of reference. This term here is in the absolute frame of reference. And again, I remind you that these absolute and relative terms can be expressed as follows, where we have the absolute velocity relative to a fixed observer is equal to the relative velocity relative to the control volume plus the velocity of the control volume itself. And sometimes it's helpful to know that if our control volume is rotating about a fixed axis, we know that this will often be expressed as omega crossed with r. Essentially, the angular velocity multiplied by the moment arm, or multiplied by a position vector r, will give us the linear velocity of our control volume at a given point, r away from the axis of rotation. And at least in this course, what we're going to do is assume that all problems are steady. So we are really only going to be looking at these terms over here. Okay, so let's have a look at a problem. Here we have water entering a rotating lawn sprinkler through its base at a rate of 1 liter per second. So essentially, the water is entering from below the page in the K direction. The sprinkler has 2 arms, each with an exit area of 30 squared millimeter, located at a radius of 0.2 meters from the axis of rotation. And we are also assuming that the water is exiting tangentially. What we want to try to find is the torque to keep the sprinkler stationary, the torque needed to keep it at a constant rotation rate of 500 RPM, and the speed of rotation if no torque is applied. Okay, so we've set up our control volumes here. In this image over here, we're looking at the sprinkler from above, and we have the control volume rotating counterclockwise. And because it's rotating in the counterclockwise direction, you'll notice that we have a coordinate system here defined by unit vectors in the radial and tangential direction, r and theta respectively. And you'll notice that theta is in the tangential direction, in the direction of rotation of the control volume. We have the velocities exiting tangentially from the sprinkler. And here at the bottom, we show the control volume from a side view with the entering flow from the bottom, which is given to us as 1 liter per second. Okay, as is always good practice, we can start with the conservation of mass as a first step. So we know that the conservation of mass for a steady problem is just equal to this statement here, which tells us that the net mass flow rates should equal to 0. So let's have a look at what we have here. Let's start with U1. So we're going to look at this exit over here. So we know that the relative velocity is going to be equal to minus q over a1 in the negative theta direction. Okay, so we have the negative because theta is positive in this direction and our velocity exiting is in the negative theta direction. and the magnitude is just my flow rate over the cross-sectional area. We know that N1 is in the negative theta direction. So, taking the dot product over here, we find that UR1 dotted with N1 is equal to Q1 over A1. Not a particularly surprising result there. So we can do the same thing for the other control surfaces. So let's have a look at that. So we have UR2 dotted with N2 is going to be equal to Q2 over A2, and UR3 dotted with N3 being an inlet is going to be negative. And so looking at this statement over here, what we find is that we have the mass flow rate out which just tells us that the net mass flow rate must be 0. And given that this is an incompressible flow, we can also say that the net volumetric flow rate needs to be 0, namely Q is equal to Q1 plus Q2, where Q is, I guess we could say Q3. This one over here. And because these are all symmetric, we can also say that Q1 is equal to 1/2 Q, which is equal to Q2. Okay, let's have a look at the angular momentum equation. So as we said, we're going to have the surface integral of the angular momentum multiplied by the flux So we need to work out these absolute velocities over here. So I'll remind you that, let's say at control surface 1, our absolute velocity is going to be our relative velocity plus the linear velocity of our rotating control volume, which we know is given by this cross product here, which is this just gives us the velocity of the CV, which we have seen before. So applying what we know, So for UR1, we've already established that it is minus Q over 2A E theta, so it's in the negative tangential direction. And plus omega R naught E theta. And this comes from the fact that omega is in the positive k direction, and R naught is just equal to R naught in the R direction. So carrying out that cross product, we get this result here, which we can express as minus Q over 2A plus omega R naught E theta. And precisely the same result is going to be found for U2. So minus Q over 2A plus omega R naught in the E theta direction. And I would encourage you to just try it out for yourself. And so we can take these cross products to work out this first bracketed term. So we have R1 crossed with U1 will be R naught in the R direction crossed with omega R naught minus Q over 2A in the tangential direction. And so working out this cross product here, we find that we have omega R naught squared minus Q R naught over 2A in the K direction, and we get exactly the same result for R2 crossed with U2. Omega R naught squared minus Q R naught over 2A in the K direction. And we know for control surface 3, namely the inlet at the bottom, with R being 0, we're just going to have R3 crossed with U3, and that is 0. Okay, so all we need to do now is work out these terms of multiplying the angular momentum per unit mass multiplied by our fluxes that were found earlier. So we want these three terms. So what will they look like? So for control surface 1, we found that the cross product is omega R naught squared minus Q R naught over 2A in the k direction. Then we need to multiply it by the flux. And so we found this UR dotted with n term. These were found over here. And so this will look like rho Q over 2. And so this is for control surface 1. And then similarly, we're going to have rho Q over 2 omega R naught squared minus Q over 2A in the k direction. The third control surface, being the inlet, is 0. And as we stated at the outset, all of this is equal to the moments about the axis of rotation in the k direction. And this would likely come from, bearing friction or something like that. And so we can simplify this. Well, firstly, we see that everything is in the k direction, so we can just drop that and assume that any result that is positive is in the counterclockwise direction. And we see that adding these two first terms, so we have rho Q omega R naught squared minus Q over 2A R naught is going to be equal to the net moment. So substituting what we know, we have the entering flow rate. We know that R naught is 20 centimeters or 0.2 meters. We seek to answer these three questions. So to keep omega is equal to 0, we just drop this first term in the bracket, and we find that we need to apply a moment of minus 3.33 Newton meters. Okay, and this should hopefully make sense, right? The momentum out of the control volume is really trying to get the sprinkler to rotate in the clockwise or counterclockwise direction. And so in order to keep it stationary, we need to apply a negative moment. Now looking at the second case, for omega is equal to 500 RPM, we find that we need to apply a moment of minus 1.24 Newton meters. And I'll just remind you that you will need to convert from RPM to radians per second in this case. And hopefully this result also makes some intuitive sense. We shouldn't need to apply as large a moment as in the case to keep the sprinkler stationary. Now, if we were to apply no bearing friction whatsoever, we can solve for omega, which is the last question, the speed of rotation. And what we find is that we will get 796 RPM. Okay, so we introduced angular momentum for fluid mechanics, for fluids problems. We are focusing solely on steady state problems in rotating frames of reference. And then hopefully it is fairly clear that looking at the angular momentum as opposed to the linear momentum is much more amenable to rotating problems such as these ones. And then in the end, we still apply all of the same knowledge that we've learned in control volume theory, but albeit in a different coordinate system, namely the radial and tangential directions and in the k direction. But otherwise, you have all the tools to be able to solve such problems.